Okay guys, Sir DB is here again. So I'd like you to listen to the continuation of my lecture on equilibrium method yield line theory. So we have discussed, I have discussed some important notes on how shear forces are distributed earlier, no? In the yield lines, along the yield lines of a slab segment. So now we deal with how the magnitude of uh, how these nodal forces, those nodal shield forces, are analyzed, no, in order to get the magnitude uh, needed for us to use on uh, the equilibrium procedure. So remember that we need these nodal forces to be used on the actual summation of moment along the choice, the axis of rotation of our choice. No? And we need to first to deal with the simplest scenario wherein we are to encounter two yield lines intersecting at a common point, and we call this the junction. No? So this is now the junction between two lines. So if there are two yield lines, we need to come up with the bending moment and torsional or twisting moment. And okay, so we have here an MB, uh, which is actually indicated here as your MB1. And I choose an axis of rotation arbitrarily or axis of moment EC, okay, and assume that at this particular point there must exist also, although this is not a yield line, there exists a moment, no? A uniformly distributed bending moment MB2 and MP2, okay, along this line. So if I have an angle of phi subtended between the two yield lines AB and AC, okay, um, and I assume a differential, a very small angle GP uh, at the other, okay, at the other interior angle, then I can make use of a simpler triangle in this regard. Okay, so if I extend this line here and I make a perpendicular line down here to there, so I may now use this triangle as my basis for moment. Okay, so this triangle here that you see is now the triangle here that I made. Okay, so this is now the triangle upon which we only need to make use of what? Geometric or trigonometric resolution of moments or forces along and about the axis of moment. Okay, I use here a double arrow symbol for the torsional and the bending moment. Okay, so if I know the value of MB1 and MB2 here, I can simply solve for MB bar. Okay, so MB bar is actually the resultant, okay, vectorial resultant of your moments MB1 and MB2, and MP bar is the resultant of your uh, torsional moments MP1 and MP2. Okay, so we now reduce a difficult geometrical shape into a more simpler geometry in this case, wherein the phi angle which is originally, okay, originally located, okay, at this point was actually transferred in terms of your phi angle here. So this is just interior angles, and this is an exterior angle. No? So if I will add phi and d phi there, my exterior angle will simply be equivalent to phi plus d phi, because this is 180 degrees minus this 2. Okay, and if these are supplementary angles, then uh, this angle here will simply be equivalent to phi plus d phi. Okay, so this is now my new angle uh, of interest. No? That's why I may now come up with the components of this m bar b. This is actually m bar b, or rather mb coming from m bar b. Take note that mb is m bar b multiplied by the length of AE. Okay, so whatever is the length of this one, because we're talking here of this MB and M bar B and M bar T as the resultant of your MB1, MB2, and MT1, MT. Okay, so we forget all of those and concentrate now with your MB and MT capital. No, so what is the difference between M bar B and M bar T? So these are in units of kilonewton meter per meter, while this will be in units of kilonewton meter, or in terms of kip. This is kip foot per foot, or and this is in terms of kip foot or foot cubes. Okay, so if we take a look at this triangle now, it's not very difficult to say that your moment, so we have been using a double arrow symbol here. Double arrow means your thumb directed to the arrowhead, and the curl of your fingers will be the basis of your moment direction. So if I make use of this and I want to resolve it, because I want to take this as my moment of axis, then my phi plus d phi can actually be made congruent to this angle here. Hence, if this is mt, then my resultant of mt, or sorry, the component of mt here will simply be equal to mt the sine of t plus t. And for mb, this is your moment of interest, so this is actually the cosine of t plus t. So adding this as your moment, okay, so take note of the sign rather, so this must be on the other side, no? So this is mt, okay, so your mb bar or m bar times ae, which is your capital mt, okay, so multiplied by cosine of phi plus d phi. Okay, so this is cosine, this is the angle and this is the cosine, phi plus d phi, plus your mt times ae. Sorry, this is mt, okay, so this is m multiplied by the sine, this is the sine. Okay, so this is the uh, cosine of P plus dphi. So we'll now be counteracting the force QA, which is, of course, our main concern at this junction or at this node. So you have a QA here multiplied by the moment arm, which is simply this length here. Okay, so whatever is this length here, from here, this is simply uh, A E, the sine of phi plus dphi. So this must be a sine of phi plus dphi. Okay, so AE will cancel, and sine of cosine over sine will be cotangent, while sine over sine will be 1. So your simpler equation for QA will now be this one. And when dphi, that very small angle, approaches 0, okay, we're talking here of an axis EC coinciding with AE, because dphi is 0, then your equation becomes a simpler equation in the form of QA equals m bar b cotangent b plus m. Take note that, again, m bar b is simply the vectorial sum of MB2 and MB1, and MP is the vectorial sum of MP2 minus M. Okay, so the junction of the three yield lines now will be founded on this uh, theory, and that I will be discussing to you on my next video. Thank you for listening and have a nice day.